This is going to be the lecture over Chapter 7 of the Physics and Technology of Radiation Therapy. What we're going to do here is go through the chapter summary so you have an idea as to what it is that we're going to be covering. And then we're going to go through the individual sections here so you have a little bit more in-depth idea as to what all of this mess is that we're talking about. So first we're going to cover exposure. Exposure is going to be the measure of the ability of photon radiation to ionize air, and we'll go through a lot of this definition and whatnot, but just know that this is going to be the first concept we're going to encounter. Charge particle equilibrium. If each charged particle of a given type and energy leaving a volume is replaced by a charged particle of the same type and energy entering, then the volume is said to be in charge particle equilibrium. In other words, you're having as much leaving of this particular type as you have entering. When a CPE, CPE prevails in a certain mass of air, it becomes easy to measure the exposure. You measure the total charge in that particular mass, and that gets back to what we were talking about there previously. Fluence. Fluence, this capital letter of phi, is going to be the total number of particles entering a sphere of small cross-sectional area A. In other words, how much stuff you have going through in a particular area. That's what this is going to be discussing. Karma, kinetic energy released per unit mass. This is an especially important topic. So karma is a medium at a specified point, and this is going to be the equation, and we'll be discussing the sum of all initial kinetic energies of all charged particles liberated by uncharged ionizing particles in a material of mass m. Now, the units of karma are going to be joules per kilogram. In other words, how much energy are you depositing in a particular amount of mass? And it may not be a measure of biological damage because it does not necessarily tell us how much energy is absorbed locally. You're going to have attenuation coefficients where we'll get into that a little bit later. You've got the absorbed dose, where you're looking at E sub AB is the total energy absorbed from ionizing radiation inside a mass M of material. And the units of dose are the same as the units of karma. So these units, joules per kilogram or gray, is going to be the same units here. And the gray is going to be the SI unit of dose. An old unit that is still sometimes used is going to be the rad, where 1 rad is equal to 1 centigrade. Dose is going to be equal to the collision karma, where the charge particle equilibrium holds. And again, we'll get into all that a little bit later. Absorption of energy from indirectly ionizing radiation, photons or neutrons. It's a two-step process. So you got your photons or neutrons coming in, karma gets deposited, it liberates charged particles, which is where the dose comes from, and it's locally deposited energy. Buildup and skin sparing. This is going to be something that's going to be important that you'll actually be able to see in the clinic. So for MVs, the relative dose to the skin is going to be low, and the dose build up to a maximum value, which is what you're seeing here, at a certain depth, d sub m, and then declines with increasing depth. The depth d sub m is approximately equal to the maximum range of the electrons set in motion by the photons. So in other words, the photons come to the skin surface, you start to see scattering going on, and then these electrons that start to scatter go in different directions, and then when you finally hit the maximum range here is where you see the maximum amount of dose be deposited. At the depth of d sub m and beyond, there is approximate CPE. So from this point on, you are looking at charge particle equilibrium. There is no discernible buildup for low energy photons because d sub m is very, very small. And if you look at the KeV energies, the superficial or whatnot, you can understand that. For cobalt-60, with a mean photon energy of 1.25 MeV, d sub m is approximately half a centimeter. Dose to air, the dose absorbed by air can be related to the exposure, and this is how that is done. Air kerma is equal to the dose absorbed by air in charged particle equilibrium. Dose to a medium, the dose absorbed by a medium can be related to the exposure in a small air test cavity carved out of the medium. The dose is given by d sub med, or med, in centigrade is equal to some function here of med times the exposure times A, which is the fractional attenuation of photons due to the presence of the medium. So in other words, you have several different factors being multiplied here. F sub med is going to be the Rankine to rad conversion ratio, which depends on the medium and the beam energy. And X of R is going to be the exposure measured in Rankines if the medium is replaced by air cavity. At low energies, the photoelectric effect is important. So at 100 keV, the Rankine to rad conversion ratio from bone to muscle is about 1.8. High energies, where the Compton effect starts to dominate, the energy density of bone is somewhat smaller than the energy density of water. And at 1 MeV, the Rankine to rad conversion ratio, F of bone over F of muscle, is about 0.94. So we've got air, medium, and then dose in free space. So the dose in free space is the dose delivered to the center of a sphere of a medium just large enough to be in charged particle equilibrium, CPE, that is surrounded only by air in free space. So for cobalt-60 radiation and a medium composed of water, the sphere would be 0.5 cm in radius, just large enough to guarantee CPE at the center. And remember that came here, that 0.5 cm happens to match the mean, or the d sub m, the depth max dose here for cobalt-60. So it's a lot of information, but that information is important. So that is what it is we're going to be going over. So now let's get in and let's do a couple of sections here, or maybe 3, so we can kind of break this up a little bit. All right, first sentence here. It's important to correlate patient treatment volume with the amount of radiation received. So we need to develop quantitative measures of the characteristics of radiation. So that's what we're trying to do. So we want to describe the intensity of the radiation, its ability to ionize matter, the energy absorbed, and the biological damage that results. What we started out with wasn't exactly the best way to do it. So over the years, we had a lot of people think about what sort of conceptual framework we needed in order to be able to accomplish this task. So we're not discussing quantities of interest for radiation protection here. We'll go forward with that later. And this is the conceptual framework. And in chapter 8, we'll talk about the instrumentation that goes along with this. So for exposure, exposure is going to be the measure of the ability of a photon beam to ionize air. That's what we see. You put a photon beam out in the air and we see ionization. How do you quantify that? So the exposure is going to be equal to the amount of all electrical charges of one side of all ions produced in air, wherein all electrons liberated by photons in a small amount of dry air of mass m are completely stopped in air. Now that's a lot to say, so let's go over it again. X is equal to Q over M. Q is going to be the sum of all electrical charges of one sign on all ions produced in air when all electrons liberated by photons in a small volume of dry air of mass m are completely stopped in air. So it's necessary to find and count all charge liberated as a result of the photon interactions in M, regardless of where that charge ends up. These electrons produce ionization tracks, like this. So you got your photons coming in here, and they're liberating these electrons. These electrons are bouncing this way, that way, and whatever else. these produce further ionization along their tracks. So in other words, as they're going out, more ionization is produced. And note that most of the ionization is produced along the tracks of the electrons. So all of this ionization coming from tracks originating in M must be counted in the definition of exposure, even though many of the ionization tracks will pass out of the volume of mass M. Each energetic electron set in motion by a photon can cause tens to hundreds of thousands of ionizations along its track. A single 1 MeV electron can produce about 30,000 ion pairs if you go back and you look at 6.4. So exposure is a measure of the ability of photon radiation to ionize the air. Exposure is only defined for photons. It's only defined for ionization of air, and exposure is not useful above 3 MeV because of the conditions necessary for measurement, which is something we'll get to a little later. Units of exposure, since it's charge over mass, you might imagine coulombs divided by kilogram, and that is the SI unit. More commonly, you're going to end up seeing the Rankine used, and that's 2.58 times 10 to the minus fourth coulombs per kilogram. For radiation protection and imaging, the Rankine is rather large and is sometimes more convenient to use millirankines. The apparently arbitrarily numerical value arose from the original definition of the Rankine in terms of rather antiquated units. So 1 electrostatic unit divided by the mass of 1 cubic centimeter of air at 760 torr at 0 degrees Celsius. So the electrostatic unit is an old unit of electric charge, and 760 torr of pressure corresponds to the nominal atmospheric pressure at sea level. Under these conditions, a cubic centimeter of air has a mass of this amount. When these units are converted to SI, the result is the numerical value in equation 7.3. So, illustration of a calculation involving exposure appears in 7.1. So, if you've got entrant skin exposure for diagnostic radiographs, if you're looking at 10 millirankine, then that's 110 kVp at 3 MAS. 300 millirankines for a lumbar spine exam, and then you've got 200 for a skull film. So you've got an example here. Volume of 1 cubic centimeter of air is irradiated by X-rays if the exposure is 1 Rankine. And if the density of the air is this, what is the ionization charge produced by the X-rays? So the charge, basically, if you take the formula and rearrange it, you can come up with this. So you need to use consistent units. So the Rankine is equal to this. The mass of the air and density of volume is equal to this. You multiply that by how much air that we've got. So it's the density multiplied by the volume will give us the mass. And it comes up to be this number of kilograms. See, this is the charge per kilogram from the Rankines. This is the amount of mass that you've got. You go through and you do the multiplication. So the amount of charge that's liberated is 0.33 nanocoulombs. Not a lot, but obviously something. So now let's go over 7.3, and then we'll do the lecture of the other sections here following in a subsequent video. So charge particle equilibrium, CPE. The definition of exposure requires that all of the charge Q produced by the photon interactions in M must be measured regardless of the final location of this charge. Figure 7.1 illustrates that much of the charge may reside outside of M. Furthermore, charged particle tracks originate outside M will create ions inside. So in general, we're facing the necessity of locating all electron tracks originating in M and summing all of the charge generated along those tracks. At the same time, we must exclude the charge associated with the tracks originating outside M. That is very difficult to do. So we've got a condition here called electronic equilibrium, or CPE. So in a radiation field, if each charged particle of a given type and energy leaving a volume is replaced by a charged particle of the same type and energy entering, same going out as the same coming in, then the volume is said to be in charge particle equilibrium. It doesn't make sense to say that CPE holds unless the volume concerned is clearly specified. So when this prevails, it becomes easy to measure exposure. We don't need to worry about electron tracks leaving the volume because any track that exists is replaced by an identical track entering. So for the same reason, we don't need to worry about tracks entering. Each one is replaced by one that's leaving. Under these conditions, we can measure exposure by simply measuring the total charge inside the volume of the mass. That's why CPE is so important. So you don't have an imbalance. You're not worried about not counting things or double counting things. This is fairly common. So for photon energies above a few MeV, however, it requires a volume of air that's so large that you just can't do it. So that's why they put a limit on it of 3 MeV. So we'll start up here with 7.4 in the next video.